Well, here we go. CCC4, Chapter 2, Connecting to the WAN. Well, it's a good one. I don't know if it is or not. It's the base of all the other ones, or all the other WAN technologies at least that we're going to go against. So, describe the purpose of a WAN. Describe WAN operations. Describe WAN services. Compare various private WAN technologies. Compare various public WAN technologies. Select appropriate WAN protocols and services for a specific requirement. Alright, we're just going to skip through this one and keep going. Purpose of WANs. Alright, so hopefully you remember, we went over this in CCC1. So hopefully you recall, a WAN is a wide area network. And so what does it do? It sends connections over a large geographical area. Typically it's at the layer 2. Sometimes they do layer 3 nowadays, but it connects remote sites to a headquarters, or remote sites to remote sites, I guess. If everything's spaced out evenly, everything is a remote site. WAN is owned by a service provider. An organization must pay a fee to use the provider's network and services to connect remote sites. That's basically all you need. Without WANs, LANs would be a series of isolated networks. That's true. Okay, so that's fine if we have a small business, but if we have a regional or branch office of an organization, we need to be able to communicate and share data with the central site. Organizations need to share information with other customer organizations. For example, software manufacturers routinely communicate product and promotional information to distributors that sell their products to end users. Employees who travel on a company business frequently need to access information that resides on their corporate networks. And now we're talking about home users. Consumers now communicate over the internet with bank stores and a variety of private. I'm sure you've never thought about that. Students do research for classes. I don't know about that one. By accessing library indexes and publications located in other parts of the country. Okay. Real great slide. Alright. So, evolving networks. What are we talking about here? We're doing span engineering. Watch how the network requirements change as the company grows. Okay. First, it's a small office. Alright, so our small office. What is our WAN connection? Now, it's not a WAN line. Okay, so this is the internet, and if we need to connect there, we're going to a website or something like this. You notice we're not connecting to another site. If we did, we'd use a VPN, and so we can go over the net. But okay, so WAN lines or private lines are typically $250 on average per meg, whereas internet is more like $5 per meg, I believe. And I don't know what the new numbers are. This has been a few years back. And so they're just using DSL and everything's hunky-dory. They're getting bigger. Alright, so then they expand out to a campus network. Alright, so now they're still connecting to the internet because they don't have any remote sites, so if they need to, access the internet, they're right here. But now they're split into different departments. Alright, so we have our campus network. Okay, so now we grow, and oh no, branch networks. Now we have several campus networks in different areas, and they need to be connected. And so how do we connect them? Through this internet WAN. And now we have people worldwide, and that was it. Anyways, WANs in the OSI model, as you can see, they're at layer 1 and layer 2, specifically layer 2. Actually, MPLS can also be, it's like 2.5, so it can form a layer 3 VPN as well as a layer 2 VPN. Anyways, these are so we were using Ethernet. Okay, so these other, now Ethernet WANs use Ethernet, but we were just using Ethernet. And so Metro Ethernet, remember, it uses Ethernet WAN. So now it's on here, but typically it used to not be. So when we see these MPLS, VSAT, broadband, frame relay, PPP, HDLC, we can just say this is just a different layer 2 encapsulation, which means our layer 2 frames are going to be specialized for that encapsulation, a little bit different than on Ethernet, unless it is Ethernet WANs. So, yeah, that's the most important part of here, of what that's saying. Just remember they run at layer 2, they do that. Okay, now we have our silly terms. Well, they're not silly, they're great. So we have CPEs, alright? So the devices that are inside customer premise equipment, the devices that are inside wiring located on the enterprise edge connecting to a carrier link. The subscriber either owns the CPE or leases the CPE. This would be an example, would be a cable modem. From the service provider, a subscriber in this context is a company that arranges for WAN services from the service provider. Alright, we have the DCE equipment. Okay, so DCE is the controller, also called data circuit terminating equipment. The DCE consists of devices that put data on the local loop. The DCE primarily provides an interface to connect subscribers to a communication link on the WAN cloud. DTE, the customer devices that pass the data from a customer network or host computer for transmission over the WAN. The DTE connects the local loop through the DCE. The demarc point, a point established in a building or complex to separate customer equipment from service provider equipment. So this just tells you, is it my problem this is down, or is it their problem, right? So our demarc is right here, this dotted line. The local loop, the actual copper fiber cable that connects the CPE to the CO of the service provider. The local loop is also called the last mile. Last mile is the most expensive part of being an internet service provider typically. The CO, the local off service provider facility or building that connects the CPE to the provider network. And then a toll network. This consists of long haul, all digital fiber optic communication lines and switches, routers, and other equipment inside the WAN provider. So that's what's allowing it to go along. So if we look at this, the router providing internet to our networks inside the company, the subscriber, is the DTE. Alright, the DCE, this is usually probably a modem or something like that, but I usually consider this side the DCE. Then we have our demarc. Okay, so we got to make sure this is powered on, but if we're not getting connection to here, it's on the other side of the demarc. Okay, and so then it is the cable provider's problem. And so they run the local loop, they own the local loop, and that runs, I don't know, through telephone lines, underground, something like that, to the CO switch, right? And then the CO throws it on the toll network to send your traffic wherever it needs to go. And yep, that's all we're studying on this entire thing, right? So common WAN devices. Yeah, dial-up modems, super common. Nope. Alright, access server concentrates, dial-up modems, alright, it's what they dial into. Broadband modem, DSL or cable modem, both operate in similar manner to voice band modem, but use higher broadband frequencies and transmission speeds. CSU DSU is a digitally leased line that required a CSU DSU. A CSU DSU can separate a device like a modem, or it can be an interface on the router. The CSU provides termination for digital signals and ensures connection integrity through error correction and line monitoring. The DSU converts the line frames into frames that the LAN can interpret, and vice versa. WAN switch, a multi-point internetworking device that is used in a service provider network. These devices typically switch traffic such as frame relay or ATM and operate at layer 2. Router provides internetworking and WAN access interface ports. Alright, so that's our important thing. Remember, the main thing, one of the things that switches can't have that routers can, are WAN ports. These interfaces may be serial connections, Ethernet, or other WAN interfaces. With some types of WAN interfaces, an external device such as a DSU, CSU, or modem, analog or cable DSL is required to connect the router to the local service provider. Core router multilayer switch. A router multilayer switch that resides within the middle or backbone of the WAN rather than at its periphery. To fulfill this role, a router or multilayer switch must be able to support multiple telecommunication interfaces of the highest speed used in the WAN core. It must also be able to forward IP packets at full speed on all of those interfaces. The router or multilayer switch must also support the routing protocols being used at the core. Yeah, no brainer. Alright, so we see everything they're talking about here, right? We have our hosts, and they're going into modems. These guys are dialing into this access server, gross. And then these guys are using DSL over the PSTN, right? And so it's ADSL, or yeah, it's ADSL. And then we have our cable, right? Going to cable, and basically all connect. Probably not realistic, but at some point they're going to connect. Anyways, but then we have these fast switches to make sure that they can handle all of the traffic. Neat, right? Yeah, I thought so too. Okay. So one type of switching is circuit switching. This is where we actually build a circuit, right? So like 56K says, hey, we're taking this path. Alright, so calls in, one side has to answer, the other side has to answer. It's very secure. Okay, so it's either the two most common types of circuit switch WAN technologies are public switch telephone network, PSTN, and the integrated services digital network, ISDN. Alright, and those are our two circuit switched. Then everything else is packet switched, and packet switches means, well, I think you guys can figure out because we've been studying packets, but it doesn't have to, it's always on, right, and it can take whichever direction. So if you have to dial in, it's circuit switch. If not, it's not. So then there's two types. We have connectionless systems. Full addressing information must be carried in each packet, right? So that's IP. And then we have connection-oriented systems. The network predetermines the route for the packet, and each packet only has to carry an identifier. The switch determines the onward route, and that'd be probably something more like MPLS or definitely frame relay. That's what it talks about down here. Frame relay forms virtual circuits, and they're passed along. The DLCs are passed along this pipe. Alright, so here's our WAN options. Private, this is our expensive stuff. Okay, super expensive. Alright, so private, dedicated. Alright, so dedicated, our lease lines, T1s, T3s. We'd probably do an OC in there if we wanted to. Alright, so those are just lease lines. That's going to be synchronous technology. Then we have our switched, and they can be switched two ways. We just talked about circuit switch or packet switch. So circuit switched, as we said, are our PSTN or ISDN, which also could be T1s, I believe. That's just T1s over the digital network. Then we have packet switch, Metro Ethernet, MPLS, frame relay, ATM. Yeah, it's the good stuff. Or stuff we use at home, the public WAN, which is the internet, right? Which we call broadband VPN. That's how we're going to connect to different sites. And we would use DSL, cable, or wireless internet services to do such a thing. And there they all are, right? So, yep. Oh, we talked about that. Alright, so here's something that we won't talk about very much, but we have DWDM, which is it dense wave or dark wave? Dense wavelength division multiplexing, okay? So this is used over SONET, right? SDH, this other thing's used in Europe. sonnets, what's connecting our fiber around here, right? So as you can see, it's just splitting. Let's give you the better definition. DWDM multiplies the amount of bandwidth that a single strand of fiber can support, as shown. Enables bidirectional communication over one strand of fiber, can multiplex more than 80 different channels of data, wavelengths onto a single strand. Each channel is capable of carrying a 10 gig multiplex signal, assigns incoming optical signals to specific wavelengths of lights, i.e. frequencies, can amplify these wavelengths to boost the signal strength, supports sonnet and SDH standards. Alright, so that's just what it's showing you, is it's what's allowing our long range fiber that connects the world to connect the world. Lease lines. When permanent dedicated connections are required, a point-to-point link is used to provide a pre-established WAN communication path. Lease lines have blah blah blah. Okay, the advantages of lease lines: simplicity, point-to-point communications links require minimum expertise to install and maintain. Quality, they usually offer high service quality because they are extremely expensive. Availability, constant availability is essential for some applications such as e-commerce. Point-to-point communications links provide dedicated capacity, which is required for VoIP or video over IP. Alright, so the downfall, the cost and limited flexibility. They're only point-to-point, so they're only going from one spot to another, and they're going to cost you a lot. And they're doing a T3 through a service provider, right? So all this device is going to think that it's connected directly to this device, even though it's spanning large areas, just like a switch, right? So these are layer 2 technologies, and so a switch also is layer 2. So if we connect two routers together, they're in the same network. They think they're in the same network. They basically think they're directly connected, right? That's what all these technologies are doing. Dial-up. I really, although few enterprises support dial-up access, is still a viable solution for remote areas with limited WAN access options. Sure, that's all we're going to go with. Bad. ISDN, Integrated Services Digital Network, is a circuit switch technology that enables the local loop of the PSTN to carry digital signals. ISDN changes connections of the PSTN from carrying analog signals to time division multiplexing digital signals. TDM allows two or more signals or bit streams to be transferred as the subchannels in one communication channel. The signals appear to transfer simultaneously, but physically the signals are taking turns on the channel. So there are two types of ISDN, and they are basically T1. We have BRI, Basic Rate Interface. ISDN BRI is intended for home and small enterprise and provides two 64K or 28K channels and a 16 KB D channel. They used to call this ADSL. Well, no, it wasn't ADSL. I guess it was just ISDN pre. And then we have pre. ISDN is also available for large installations in North America. PRI delivers 23 B channels with 64K and one D channel with 64K, equaling the same speed as T1. And there you have it. Although ISDN is still an important technology for telephone service provider networks, it is declining in popularity as internet connection options with the introduction of high-speed DSL and other broadband services. Basically, they're faster now than those, so why would you use them? Okay, here we go. We have frame relay. It's awful. You're going to have to program it. You'll never see it. It's very old. So basically, it forms virtual circuits. So it says this delc goes to this delc. It's just a layer 2 tagging. The virtual circuit just says from here to here. Goes to this delc. Uses inverse ARP. Yeah. Frame relay creates PVCs, which are uniquely identified by a data link connection IDLC. The PVCs and DLCs ensure bidirectional communication from one DTE device to another. And they're not really showing you why virtual circuits used to be a cool thing. But what it could do is you could take, half of a T1. You could pay for one T1, so one local, one last mile. And half the speed could be connecting this branch office, and then half the speed could be connecting another one. And so it's what we call, that's why it's a non-broadcast multi-axis, because we can put multiple on there. It doesn't have to be point-to-point like before. Okay. So whenever you see NBMA and EIGRP or anything like that, that's what it's talking about. ATM, asynchronous transforward mode. Technology is capable of transferring voice, video, and data through private and public networks. It is built on a cell-based architecture. That's the most important part. Whenever you hear cell, and it's a 53-byte ATM cell, that is the only questions you'll ever be asked on ATM. It's just another layer 2. It's great. A typical ATM line needs almost 20% greater bandwidth than frame relay to carry the same volume of network data. ATM was designed to be extremely scalable and support link speeds of T1 to OC12, 622 meg. Alright, once again, it's kind of losing. ATM offers both PVCs and SVCs, although, okay, so PVCs, I believe, so that'd be a static virtual circuit, where SVC is dynamic, I believe. Read on the last page, but I'm pretty sure that it is. PVCs are more common with LANs. As with other shared technology, ATM allows multiple VCs on a single lease line, the connection of the network. Ethernet WAN, this is where we're just doing Ethernet. These are Metro Ethernet providers. This is probably the most common nowadays because you get super fast speeds, and use MPLS with it. As it says here, Ethernet WANs have gained in popularity and now commonly being used to replace the traditional frame relay and ATM WAN links. Alright. Anyways, let's see. Reduced expenses administration. Ethernet WAN provides a switched high bandwidth layer 2 network capable of managing data, voice, and video all on the same infrastructure. Increases bandwidth and eliminates expensive conversions to other WAN technologies. Easy to integrate because we're already using Ethernet. Enhanced business productivity. Ethernet WANs enable businesses to take advantage of productive enhanced IP applications that are difficult to implement on TDM or frame relay networks, such as hosted IP communications, VoIP, and streaming and broadcast video. MPLS is a layer 2 protocol, and it's can carry any payload, including IP version 4, IP version 6, Ethernet, ATM, DSL, frame relay, blah blah blah. That's why they call it multiple protocol label switching. It is a high-performance WAN technology that directs data from one router to the next based on short path labels rather than IP addresses, right? So it says, oh, this label goes here, this label goes here. When we do frame relay, it'll make this look a little, it'll seem, hopefully you can understand it. MPLS, it's expensive, it goes off lease lines, blah blah blah. And it supports a wide range of WAN technologies, including T-carrier, E-carrier links, and so it's telephone and fiber, I believe. Carrier, Ethernet, ATM, frame relay, and DSL. SAT, oh no. Okay, so why is it slow? We have to go to space to get it, but sometimes we have to use it because there's no other choice. So if we have a line of sight to the sky, and that's our only choice, that's what we're doing. But usually we have to pay per meg, per download. Like it's very limited. So DSL, we have our always on connection with DSL. DSL is always on, twisted pair, goes to the DSLAM. Alright, where was I? Oop. What's going on here? Get that crap out of my face. Sorry about that. And back to our DSL. Alright. So, their DSL technology, blah blah blah. Okay, keys. DSL is key to you. The closer to the D-SLAM, the better. Okay, so multi-DSL subscriber lines are multiplexed into a single line, high-capacity link using DSL access multiplexer. The D-SLAM at the provider location. D-SLAMs incorporate TDM technology to aggregate many subscriber lines into a single medium, generally a T3 DS3 connection. Current DSL technologies use sophisticated coding and modulation techniques to achieve fast data rates. There is a wide variety of DSL types, standards, and emerging standards. DSL is now a popular choice for enterprise IT departments to support home workers. Generally, a subscriber can not choose to connect to an enterprise network directly, but must first connect to an ISP, and then an IP connection is made through the internet to the enterprise. Security risks are incurred in this process, but can be mediated with security measures. Alright, so does it not tell us? We need to, there is a question about where your performance stops being as good. But so the closer to the D-SLAM, the better. That's one thing to know, right? And so the D-SLAM hits, I don't know, some kind of CO office probably, right? And then goes through here. And what they're showing is D-SLAM going through the internet, right? So your DSL connection through the internet to the corporate WAN connection and then into the office, right? And I think we all could have figured that out, but important point of presence, D-SLAM right here. That's what we're looking for. Then we have cable, right? So, cable has fun stuff too. Cable modems provide an always-on connection and is a simple installation. A subscriber connects to a computer LAN router to the cable modem, which translates the digital signals into the broadband frequencies used for transmitting on a cable television network. The local cable TV office, which is called the cable headend, contains the computer system and databases needed to provide internet access. The most important component located at the headend is the cable modem termination system, which sends and receives digital cable modem signals on a cable network and is necessary for providing internet services to cable subscribers. Cable modem subscribers must use an ISP associated with the service provider. All the local subscribers share the same cable bandwidth. As more users join the service, available bandwidth may be below the expected rate. Right, and that's why we can get, Cable One can give high guarantees, but it doesn't mean you're actually going to get it because other people are sharing that service with you. That's used to be why they called it broadband. So here we are on wireless, and here's our sample wireless technology. Wireless can encompass quite a few things. Like these ones over here, we can assume that they're using 802.11, right, to do it. Then we have 802.16 WiMAX, which is going to have a longer range and higher speeds. But let's break it down. Municipal Wi-Fi. Many cities have begun setting up municipal wireless networks. Basically, this is just where the city has wireless everywhere that you can use. WiMAX. Worldwide interoperability for microwave access is a new technology that is beginning to come into use. It's definitely in use now. WiMAX, LTE are similar technologies. I can't really tell you where they're different, but they're almost the same. But WiMAX we're seeing here. So to access WiMAX, subscribers must subscribe to an ISP with a WiMAX tower within 30 miles of their location. They also need some types of WiMAX receiver and a special encryption code to get access to the base station. Alright, so it's just long range, higher speed, wireless. Wireless, does it tell us here? To get it, we probably should be within 5 miles, depending on what we're shooting with. But anyways, just WiMAX, because it's a lot longer. Then we have satellite, the VSAT, slow, goes to space. Alright? 3G and 4G, third generation, fourth generation, right? And then we have LTE. It refers to a newer, faster technology and is considered to be part of the fourth generation. So we're actually working on 5G now. That's what they consider AC, but this has to do with other things. But it's just building up the infrastructure, right? Long-term evolution. The infrastructure has been built up, fourth generation of build-up, fourth generation of new devices, faster rates, that kind of thing. Alright, so when we go over the internet, we instead of getting a WAN, we can use VPNs. I'm sure you guys have heard of VPNs. We can use them for other things besides this. But they save money because we don't have to have a dedicated link. Secondly, they provide security. We can secure VPNs in all kinds of ways. Older mechanisms are like IPsec, which is what we'll be talking about here, but we can have SSL VPNs, all kinds of stuff. Scalability, because VPNs use internet infrastructure with an ISP devices, you add new users, right? Especially if they're home users. Just keep adding them on. As long as you have an internet connection, you're good to go. Cisco actually makes little access points that you power on. Just plug them into your home internet. They'll provide a wireless signal and form a VPN back into the company. Compatibility with broadband technologies. Yeah, they work over broadband. Okay, so then we have two types of VPNs. We have this one right here. These are site-to-site VPNs, right? Where we're actually connecting. It's a permanent link between two sites. Then we have a VPN client, remote access VPNs, right? And that's where these workers use a program probably, or they go to a website and it does a VPN into the same place, rather than like this just links two sites so they can talk to each other. This one just links the client's computer into this private network. So how it's working too is it's seeing this, right? Even though it's going over the public, this is encrypted, and it's like a 192. It's a public address that could be routed to, probably not here, but in the site-to-site definitely. But yeah, this would be still assigned a private address that the inside network, company network would know. That's why they call them a virtual private network, right? Because it's using a private network. Choosing WAN, I don't know. You guys can go through this, probably not important. And that was that one. Chapter 2 down. Some basics on the WAN. We're gonna go over a lot of this stuff more as we go through, so if you're confused, hopefully we can get that calmed down. If you have any questions, feel free to send me an email.